Well, thanks to the organizers for the invitation to speak, and good to be back in Beijing. I have chosen to talk about a recent work that I did, which is mildly technical and in a certain spirit, as you will see, not fully complete, but I felt it's quite appropriate because it was done in collaboration with an excellent undergrad from Tsinghua, Jianming Zheng, who is joining us as a PhD student in the fall. And there's a very closely piece of related work, which has almost 100% overlap by these folks, Beatrix Mollman, who's at IIS, Vladimir Novolansky, who's also at IIS, and Yanis Yares, who's in Paris. And I'll mention as we go along some ongoing considerations with Jianming, Beatrix, and Yanis. So I'm going to sort of set the stage by talking broadly about what is it that we're after and what we're motivated by. I won't end up addressing all the questions in the motivation, but you'll see some of the general principles that sort of led me to thinking about these things. So going back almost, I would say, 3.5 decades, our understanding of the worldsheet string theory, and in particular, both its dynamics at the perturbative and non-perturbative level, have been largely informed by the fact that there are low-dimensional models, not the usual critical string constructions in flat space, but the low-dimensional models which have given us a great deal of insight. For example, Marcos mentioned this concept, how we learned about the large order perturbation theory and the origin of D-branes, which came out but not by studying critical string, but rather by studying the non-critical string examples in the early 90s. And as these models, they are themselves dual to matrix models, and in some sense, they form a simple prototype for things that we know and love, like the ADS-T correspondence, which involve much more dynamically complicated matrix quantum field theories with matrix degrees of freedom. But these models are simple because they're just matrix integrals. Of course, the most famous of these is the famous C equals 1 string, or its supersymmetric version, which was discussed 2.5 decades ago. This series of works which began by McDivie and Verlinde, revisiting the 0A and 0B constructions of the C equals 1 string. And usually these strings have been sort of thought about as non-critical versions, where you have some piece of the construction which involves just the usual ingredients like a free boson, and then to make up the remaining central charge, you stick in a Liouville. But you could ask, are there simpler theories of matter that make up worldsheet strings, which have very minimal ingredients that sort of are primitive building blocks of CFTs? And one such, or by now two such, are these constructions that just use as ingredients the Liouville CFT. And 2 years ago, our friends Scott Collier, Lawrence Eberhard, Beatrix Mollman, and Victor Rodriguez came up with a very beautiful model, which they call the Virasoro minimal string, which basically has just two pieces of ingredients, a Liouville theory with central charge bigger than 25, and another Liouville theory, which usually is called the time-like Liouville theory, with central charge less than 1. And with this, coupled to the usual BC ghost system, this defines a non-critical string. And I'll say a few things about it in a minute. More recently, about a year ago, they constructed a more interesting generalization, which I won't talk about, but let me mention it in the present context. They took two Liouville theories with complex conformal dimensions, 13 plus minus I lambda, and you can think of these two Liouville theories as CPT conjugates of each other. So that this theory has interesting connections to, let's say, low-dimensional de Sitter physics. And in fact, they have been sort of, that was one of their motivations to sort of try to construct worldsheet examples which would compute from the worldsheet integrated cosmological correlators. Okay. So let me say a few words about the Virasoro minimal string and why I got interested in this. So while it's a worldsheet theory, you can view it as a particular deformation of the JT gravity theory. And JT gravity, as Sachenko and Stanford showed, is itself dual to matrix model. So in particular, this Virasoro minimal string, while its target space picture is a bit complicated, although Victor has an interesting interesting observations about it in the context, thinking about it as a sort of worldsheet description of some kind of cosmological model. This model itself is in itself interesting because it has a large web of dualities, as these folks sort of spelled out. One, it at its core, it's dual to a matrix model, but this matrix model is a deformation of the JT gravity matrix model with a spectral curve, which you can think of as a deformation of the spectral curve that comes from JT gravity. The sinh square root E curve is deformed by one parameter, and that parameter you can think of as parameterized in the Liouville theory. So in a particular limit, in the semi-classical limit of this theory, you recover back to JT gravity. Second, it has interesting connection with geometry and topology, in particular with intersection theory on the modular space of punctured Riemann surfaces, which you can work out using the formalism of Virasoro TKFT that Scott and Lorenz developed with Mengele. And it's related in the same vein to chiral 3D gravity, where you can think of the canonical Hilbert space of chiral 3D gravity as a space of being contrast on Riemann surfaces as being related to the space of conformal. So in some sense, it's sort of very primitive because it really accesses data of CFT. So what I'm going to be interested in is in a particular supersymmetric analog of this, and as a worldsheet construction, and I'm going to be interested in sort of the broad picture is to try to generalize this web of dualities arising in this context. Okay, none of these ingredients, some of these ingredients have been developed in the context of the supersymmetric version. Some of these ingredients haven't yet been developed. So what I will tell you is mostly the worldsheet construction that we've done and what we can infer from what has been developed in the context of the matrix models that Stanford and Wheaton described about 6 years ago. But I won't be able to, I won't tell you anything about these things because these are things under consideration that I don't have any deep insights on what these statements are. Okay? So to begin with, I'm going to sort of start by reviewing. Yeah, yes, please. Yes. So I'll tell you what we're going to consider and what we will describe and what is actually being done. And since you brought this question up, the discussion I'm going to tell you is going to be the simplest supersymmetric generalization. And maybe towards the end, I'll comment on higher supersymmetric generalizations. For example, in your talk, you mentioned that if you want to sort of study the physics of black holes, supersymmetric black holes, the simplest theory to study is n equals 2 JT gravity. I will mostly focus on n equals 1, which itself, as you will see, has lots of subtleties. But the n equals 2 case is a lot more interesting. Of course, there's a matrix model that Turiachi and Wheaton discussed, and the string construction is open for various reasons that you perhaps know just as well as I do. Okay, so let me begin by just reviewing what was done in this Virasoro minimal string, just so that we are on the same page, and sort of then that will also allow me to introduce to those of you who are not fully familiar just the elementary concepts of Liouville CFTs. Okay. So the bosonic Liouville theory, and throughout this talk, I'm going to take the following philosophy about CFTs, which is the sort of modern philosophy of just telling you what the basic spectral data is and what the OPE coefficients are, and by bootstrap arguing that this is a complete prescription of the CFT without sort of, while I will write down some Lagrangians once in a while, they won't be sort of central to what I'm going to say. So bosonic Liouville theory is a non-compact CFT, it's an irrational CFT, with a continuum set of primaries, and they have set of OPE coefficients, which, as I said, will just satisfy bootstrap constraints. So we'll parameterize the theory by a central charge, and we'll trade that central charge for a parameter B. Okay, so B parameter is the theory, and for my discussion, I'll take B to lie in the interval 0, 1. Okay, so B goes to 0 will be the semi-classical. And the spectrum of primaries is parameterized by a continuous parameter P, and the weights, the left moving weights, holomorphic weights of these primaries are given by this function of B and this momentum. If you just stare at this formula, the canonical domain for this theory, where for B taken to be in the half in 0, 1 is C bigger than 25, and this is usually referred to as a space-like theory. The theory can, of course, be defined outside this domain, and that's what part of what I'm going to show you later. And the natural definition, which analytically continues to complex C, exists everywhere outside the half line C less than 1, going to minus infinity. So on the ray between minus infinity and 1, you can, outside that ray, you can analytically continue the Liouville structure constant. For the ray between minus infinity and 1, you need to be a bit more careful, and that's one of the things I'll describe. Okay, so I've also tell you what the vertex operators are. And importantly, to specify the theory, I just need to tell you what the 3-point function of these vertex operators. If I take 3 of these vertex operators, parameterized by 3 different momenta, there's a particular structure constant, which is a function of momenta, given in terms of some special functions whose details we don't need to know about, but these were worked out by the famous DOZZ formula in the mid-90s and can be derived using Teschner's trick, which I will review in the sequel. Okay? So these functions are some Barnes double gamma functions which satisfy some interesting functional relations, none of which will be playing an important role in what I want to say, but so let me not dwell on. So I made some choice for the presenting the structure constant. This is not the choice you will see in the DOZZ papers. And the choice is engendered by normalizing the vertex operator suitably. So the 2-point function picks out a canonical normalization that's related to this universal, what I will call the Cardi density of states. You can think of this as the modular crossing kernel of conformal blocks in bosonic CFTs. And if you take, in some sense, this, if you write this P, since the conformal dimensions are related to P squared, if you take this formula and write it as a spectral density as a function of energy, this is sinh of square root E, and the P of E, rho of E, dE has 1 over square root E. And if you take B to 0, this becomes the famous sinh square root formula of JT gravity. Okay. So that's the connection between JT gravity and this particular matrix model. For me, PI is a positive. So sorry, PI is a second. So this is the reflection coefficient, right? So this is the sort of the P being negative for the second set. Yeah, because so it's basically the statement that I'm sort of scattering of the Liouville wall. There's one piece where it's sort of the momentum conserving piece, and one piece which is the reflected wave. Correct. So it's a conjugate operator and with the usual caveat that this particular theory doesn't have usual state operator correspondence because the identity is not part of the spectrum. Good. The statement that all we need to know about this theory is that given this data that I just told you, the spectrum and the OPE coefficients, you can just compute any correlation function on any genus G Riemann surface given in terms of just sawing together these structure constants with conformal blocks. Conformal block data is just universal. You don't need to know anything about the details of the spectra, but and then we just integrate over the intermediate momenta that show up in this. Okay. And this factor of rho 0 is just because I've normalized the 2-point function in a particular. Okay, so this is the conventional definition of the theory for central charge bigger than 25. Yes. Yeah. Yes. Yes. So those would be sort of the partition functions with some boundary states, which were worked out in that context. I will actually not talk about any other wave functions in this context. I'm going to talk only about the amplitudes. Okay, so but yes, but for now this is just the CFT. When I put together this with the next, what I'm going to show you in the next slide, that will give me some worldsheet theory, which in a semi-classical limit will have JT gravity as the low energy description. This is more like the double trumpet because it has both pieces. Yes. Good. Any other questions? Right. So that's the bosonic theory that is sort of standard. But turns out, if I want to define the theory for C less than 1, there's a equivalent parameterization. And this, of course, is also well known, going back again 2 decades, worked out initially by Zamolodchka and Kostov and Petkova, but then numerically checked very nicely in a paper by Ribot and Santa Chiara from 10 years ago. And in writing the time-like theory, I'm going to make a convention choice. I'm going to, if you can follow my fonts, anything which is sans serif will refer to the time-like theory. And I'm going to parameterize the central charge by, again, a parameter B, which now, again, is taken to be lying in 0, 1. And now the central charge is strictly less than 1. I'll define the theory with vertex operators, again, with P real. But eventually, when I write down the structure constants, as I do in the next cell, those structure constants will be related to the structure constants of the space-like Liouville theory by a particular analytic continuation. Okay. So the way these folks derived the structure constants of this theory was by realizing that you can look at the constraints coming from degenerate correlators for 4-point functions, and those constraints give you some set of functional relations for the structure constants. One solution to the structure constants is the DOZZ formula, but there turns out to be another solution to the structure constants, and I'll review this in the context of the supersymmetric theory, and those give you the structure constants of the time-like theory. And there's a nice, if you parameterize things the way I have, the statement is that the structure constants of the time-like theory are inverse of the structure constants of the space-like theory, with the B parameter replaced by the time-like B parameter, and the space-like momenta being related to the time-like momenta by factors of pi, by some analytic factor. I should, however, emphasize, although the formula for the structure constants looks like I'm just doing some inversion and some analytic continuations, these functions that I have sort of elided over in detail they're related to gamma functions, so they have lots of poles in various places. So when you actually want to sort of do the crossing checks for these equations, the integration of these momenta is not over the real line. It's over some contour that's off-shifted from the real line. So the end result is not purely an analytic continuation, but something slightly more. Okay, and I should say that this has been very well tested in many contexts. So there's some nice in recent years there's been sort of nice mathematical developments by mathematicians trying to understand how to think about the time-like theory in terms of probabilities, and also some nice work recently by Santa Chiara and friends of trying to sort of understand how the structure constants arise. It's not quite, it's something like that, but it's not quite the same thing. So I would just say that the theory is defined for C real between -infinity and 1 by these structure constants. For C bigger than 25 and other complex values by analytic continuation from the space-like theory. And there's some subtleties if you want to go to some special values. But let me take that offline. Okay. They would be like so the classical saddles for time-like theory. So they would look like Lorentzian cosmologies, right? Because so the Liouville classical potential would have a but the time-like theory itself would just have one field, right? One bosonic field with a Liouville potential. I don't think it describes a sphere. I think it describes something which either crunches or grows. Well, think of just space like Liouville theory. There's a Liouville field with a potential that sort of cuts off the strong coupling region. Now, imagine that this is a Liouville field instead of being space-like, it's a time-like coordinate. So you're scattering in some time-like direction of some potential. So either, and that's the definition of the time-like Liouville, classical Liouville theory, right on the classical Lagrangian. Which of course doesn't sort of tell you anything about the quantum theory. Yeah. Correct. It is. It is different. It is different. Yeah, that's what I meant, that for this ray between minus infinity and 1, the theory is defined by these structure constants, and it's not obtained by some simple analytic continuation in B. Yes, because it's a time-like coordinate. It's like a time-like boson, but with a Liouville potential. Yeah. Correct. Right. So the Virasoro minimal string is basically saying put these two theories together. One has C bigger than 25, one has C strictly less than 1, so you can add them up and get C equals 26. And if you sort of work out what you want, it just means that the Liouville parameters on both sides are said to be the same. So B equals. One could study that theory as well. I mean, that's another possibility. So you could study some variants of this complex Liouville field. I think you might want to worry about what CPT conjugation and things like that are, which is, I think, why the example that have been studied is this 13 plus minus I lambda, which is the symmetric case. Yes, Matthias? Which one? For this construction, yes. I was just about to say that, yes. For some cases, right? So indeed, as Matthias presaged, if you now ask what are the physical vertex operators of the string theory, what is in the physical BRST cohomology, you find that they are vertex operators of the space-like Liouville theory and vertex operator time-like Liouville theory, but with their momenta identified this way. But realize that because the structure constants of the time-like theory are related to the structure constant of the space-like theory by this particular analytic continuation momenta, this does mean that for simple correlators, the structure constant just cancel. Okay. So what happens because of these constraints on the spectrum and the physical state conditions means that, for example, the worldsheet 3-point function is a pure constant, which I can set to unity by some normalization. Okay. Of course, higher point functions require integration over intermediate momenta, both on the space-like side and on the time-like side, and those momenta don't need to be correlated. So if I want to compute higher point functions, I actually need to do some work. But there's some nice things about these worldsheet constructions. But first of all, the integrals you need to do over the moduli space to actually compute worldsheet observables are absolutely convergent, so you can do them numerically. Okay, so they don't have subtleties of physical string theory where the integrand, you can get the integrand, but then you have to sort of figure out how to actually compute it to get the physical answer, like even for example, the Veneziana amplitude. It's not, the integrand is not well defined in the physical kinematic regime. Convergence is not true. So this is not true in these examples. So what was done in this analysis so far was to show this statement, to show that the classical theory, if you take these two pieces and take the limit b goes to 0, you get back JT gravity. Then invoke the fact that there is a potential matrix model with this spectral curve, which is the deformation of the JT gravity matrix model. Use the fact that such a matrix model satisfies topological recursion to work out the observables from the matrix model, and then cross-check against the statements of correlators computed numerically from this guy. Okay, I'm going to come back to it because it's going to be important in the supersymmetric case, that these observables that I'm going to tell you about are going to be much, much simpler, but they're much, much harder to see from the worldsheet. Okay. So that's a story from the background. So now if there are questions, I'm happy to answer about the about the basic stuff, because then I'm going to switch gears and make life more complicated with supersymmetry. They are the same piece. So this VP is a vertex operator of the space-like theory, labeled by a real momentum P. This V, since you can't read my font, which is sans serif, is a vertex operator of the time-like theory, except that there I should have put a sans serif P for the momentum of the time-like theory. But that momentum by physical state condition is related to the momentum of the space-like theory to be I times the space-like P. Okay, so there's some magic happening here, which is why the thing. So maybe I will say this magic because this magic can happen once more in the superstring case. You might have said, who cares about world sheet? Liouville theories are defined as CFTs, right? And they have structure constants. The magic is the DOZZ formula and the DOZZ formula, corresponding DOZZ formula for the time-like theories, have this very funny a priori ill-posed, a priori unmotivated relation of inversion, with momenta in the time-like theory being I times the space-like momentum. Okay. However, had someone tried to do this construction ab initio from the world sheet, they have discovered that this relation is very natural for reasons Matthias just said. And what we are seeing at the level of correlators, that they sort of amplitude just cancel. 3-point function of the space-like theory times 3-point function of time-like theory is just 1. They're functional inverses of each other. And this is true from actually studying null state decoupling in the correlator. But it wasn't ordered a priori. It seems like it's much more tailored towards a string construction, which suggests something. Yes, Margaret. Yes. There's probably something deeper here that's going on. Yes, yes. So indeed, the example that you have with Lorenz recently has some similar features of this kind, which I think would be interesting to study. Yes.
I mean, we see that you can write a data like easy model, such that these two you can say
Yeah. We could do that, but then you would not project out the tachyon. So these are non-critical strings with no tachyon. So you could do something else. You could take some other combinations of Liouville and then add some other stuff that you like. Maybe you could even add a free boson if you want. But then you have an issue that the tachyon won't be projected out from the spectrum. Okay. So it's like this is like very much like the usual non-critical string construction where you take C equals 25 Liouville and a time-like boson. I just again for reasons that Qiming asked, the time-like boson is not the B goes to one, whatever appropriate value limit, or C goes to 1 limit of the time-like Liouville theory. What did I do here? I switched off the projector. No, that's not. Okay. This is not even connected with the. Yeah. So just to that's a subtlety. So here the choice between the two B's is simply to get the critical, cancel the world sheet conformal number. Okay. Good. So I just say in equations what I just said about the world sheet amplitudes. The world sheet amplitudes involve computing correlators of space-like Liouville and time-like Liouville with momenta, and so these are genus G correlators which you can compute given what I told you before. And then there's some piece coming from the ghosts that you just compute the appropriate ghost correlators, and then you integrate these over the modular space of genus G Riemann surfaces with n punctures, which is the locations that you're inserting. What are these quantities computing from the point of view of the JT gravity or its deformation? They're computing volumes of Riemann surfaces with geodesic boundaries and the boundary lengths are related to this Liouville moment. Okay, so this was a statement that was proved in the paper by Scott and friends, And the quantum volumes that they computed, they were computed using matrix models. Again, there's an interesting statement which I will just bookmark for now and come back at the very end. Namely, the worldsheet theory, if it's really dual to the matrix model, for me, a test of it would be to derive the topological recursion directly from the worldsheet. Should you be able to derive topological recursion from the worldsheet, you would have actually proved the duality, and these integrals would have been clear why they are computing these quantum volumes that these folks compute. Okay? And as I said, the quantum volumes are computed for a matrix model with this particular spectral curve. And in this way of writing it, you can see parameterized by this energy that if I take B to 0, this really gives you the JT gravity spectral curve. Yeah. The deformation by B. Correct. All I mean by quantum volume is exactly that there's a parameter B. It's a one parameter deformation of the classical volumes. Good. Perfect. So everybody on the same page with me for this discussion? Let's move on to the super case. So I'm going to review something about the super Liouville theory and then say something about how to define the time-lag theory, which wasn't done till the two papers I mentioned in the beginning, and then yeah. Yes. The dating thing, I think that's important. Yes. Yes. Yes, that analog is also exists here. So these are the simplest observables to compute, where you cut out the geodesic boundaries and then you glue. But then if you, as in the JT case, if you work out what the trumpet wave function is, then you can glue the trumpet back here and understand what that computes. So that can be computed using boundary states in that space-like and time-like case. And since I don't want to talk about boundary states, I chose not to sort of talk about it, but they did work out all those details in their paper. So I don't understand a lot of the details of the target space theory for the following reason. For reasons that we just discussed, if you think about what the target space theory is, you have a Liouville wall in one direction, in the space direction. You also have a Liouville wall in the time direction. So the best way to think about the target space would be to say you either start from some big crunch or a big bang, or you end up either start from a big bang or you end up in a big crunch, depending on how you oriented the time-lag theory, and you live in a space that's cut off by a strong coupling Liouville wall. So it's some kind of cosmology which doesn't seem to have a simple interpretation in the usual, like in the analog of, say, the minimal streak was one case, where we at least would say that there is a picture where we have a time direction and you can scatter states from the left or from the right onto the Liouville wall and back, and these you can think in terms of free fermions. That picture doesn't exist in this context. At least I think it needs to be developed, but I don't know of a better statement to make than what was made in Victor's paper. Good. All right. So let's do something supersymmetric for a second. And for the most part, I'm going to talk about theories with 1,1 supersymmetry. The more interesting case is 2,2, but that's a lot harder. And we don't know much about it, but let's talk about the 1,1. So I just wrote a classical Lagrangian just for kicks. It's just, there's now a Liouville superfield, which has a bosonic piece, which is the bottom component is the usual Liouville field. And then there's a left and right moving fermion. And if you look at the potential, the superpotential piece, this potential will basically give you something like psi tilde e to the d phi. Okay, so importantly, it's not simply a Liouville coupled to Ising, even though the central charge you can think of the ingredients as two fermions and a Liouville field. It's an interacting theory because the Liouville potential is psi tilde e to the phi. Okay? And again, I'll parameterize the theory by a parameter B, and the central charge is related to B in this way. And if you work out what the bounds on the central charge are for B between 0 and 1, the central charge exceeds 13 halves in the supersymmetry. As usual, the moment you put in fermions, you have to start worrying about boundary conditions. and you start worrying about the difference between Nebel-Schwarz and Ramond sectors. Okay. Now, things are a lot more complicated than usual critical string constructions because you have single right mover and single left mover. So you can't just put in spin fields and bosonize everything and get away the easy way. So you actually have to worry about what are the boundary conditions. And one way to think about everything is to think in terms of spin and disorder operators of Ising mode. I'm going to elide over that and just tell you what the physical vertex operators are and tell you what happens. So life is simplest in the NS sector. There's a single superconformal primary, which I will call VP because it's the sort of analog of the bosonic vertex operator. But unfortunately, unlike in the bosonic theory, because this is just a superconformal primary, it has G minus half descendants and G tilde minus half descendants, which are conformal primaries. So it has a spin half field, say, so this has some weights, which is, it's spinless, so it has left and right moving weights the same, but this guy has left moving weight up by a half, and this guy has right moving weight up by a half. But then there's a double descendant, G minus half, G tilde minus half, which is also spinless, and that's something I'll call W. Okay? And it's going to be important that there are two spinless fields in the NS multiplet. And again, I can normalize the 2-point function of these V's by some normalization that now picks out the appropriate fact. This is basically again given by the modular crossing kernel, but now for the super characters of the n equals 1 theory. So in fact, these are crossing kernels for trace in the NS sector with no minus 1 to the F insertion. And again, the momentum is real, and the weights are basically given by appropriate shifts from Q squared over 8. The Ramond sector has two degenerate primaries. They basically look like the spin and disorder operator for Ising, dressed with the Liouville field. Okay? I'm just going to call them R plus minus. And you can think of them as having worldsheet fermion parity plus and minus under a worldsheet minus 1 to the F. It's both left and right moving. It's not chiral. It's both left and right moving. Indeed. Thank you, Matthias. And they have weights which are off by 1/16, which is the right answer for the spin and disorder operators. And if you compute and I will normalize their 2-point function by a different normalization, which is with this Koch factor, which again comes out of the modular crossing kernel, but now for the trace in the Ramond sector. Okay, so that which is related to trace in NS with minus 1 to the F by modular transformations. Good. This operator does not fall into any super multiplet because it just sort of it is degenerate. It just one of them is obtained with, so one of them sort of, let's say they're related by action of G0 in the Ramond sector. Exactly. One annihilated, so one is raising, one lowering. Exactly. And because of G0, they have opposite fermion parity. That's it. Realize that at the level of 2-point functions, if I tell you what the normalization is for VP, since everybody else is obtained by action of super current generators, all the other normalizations are fixed by Bohr identities. Life is slightly more complicated if I go to 3-point functions. Okay. So there are lots of 3-point functions because you can have 3-point functions between from various pieces in the NS sector and various pieces between NS and Ramond. Spin selection only gets you so far. Turns out life is not that bad because when the dust settles, there are 4 undetermined structure constants by superconformal Bohr identities. Okay, so there are 2 in the NS sector and there are 2 in the Ramond sector. The 2 in the NS sector, the one is obvious, it's just the analog of 3 V's. So that's the structure constant of the 3 superconformal primaries. But funnily enough, 1 W and 2 V's, namely one double descendant in the NS sector and 2 superconformal primaries, is unfixed by superconformal Bohr identity. So this is a new structure constant you need to worry about. So they're there, but they're related by Bohr identities. So what I can do is I can write down a single superconformal for the whole multiplet. For the whole superfield I wrote down. For the super operator, I can write down a 3-point function. And it's best way to say it is that guy is fixed in terms of two undetermined coefficients, which are parameterized to be these two structure constants. That these are not chiral; these are the whole correlatives. Now, you can, but you have to figure out how to saw them back. You can. Yeah. There's no simple chirality in this problem for usual reasons that Liouville doesn't have simple chirality. Things do mix. But yes, you can do this. You certainly can do this. And for example, let me just bookmark a piece for you. People who've worked out superconformal blocks like Hadash and Sushanek and so on, they do have some chiral representations, but then you need to figure out how to plot them back. I'm coming to, so far it's just CFT, no string theory. Coming to GSO projection in one. Hold on to that question. Okay. Okay, so I will not. W is the, yes, is G tilde, G half, G tilde minus. They're independent structure constants. Yes, they're not related by superconformal modality. This is the most important statement I wanted to keep in mind. Okay, and there's some choice I made here for this Ramond structure constants in terms of the evens and odds, but that's some detail. Don't worry about it. I will not write down the formulas for the structure constants. These are worked out actually very soon after DOZZ by these folks, and they're known. They're known in terms of the same Barnes gamma functions. It turns out life is nicer if you sort of take particular combinations of these Barnes gamma functions, which we can put labels NS and R. But if you look at the literature, you want to know what these functions are. They're related in some simple way. For now, we don't need any of the special functions. They won't show up in the result. Okay. Okay. So I just want to review how these were determined and how the DOZZ formula was determined, just to get us on some page, because I then want to tell you how to get the answers for the time-like theory, which is new. The idea, which goes back to Teschner, is to look at the following: a 4-point function. Let's say in this particular case, we'll take two Neveu-Schwarz superconformal primaries and one Ramond primary. And I'll insert in a degenerate representation of the superconformal algebra, which in this case, at lowest level, turns to be a Ramond vertex operator. Okay. The bosonic case is just a bosonic vertex operator. It would have been V with momentum 2, 1, where that just means 2 over B plus B momentum. And the nice thing about these degenerate operators is that their fusion has only finitely many terms on the right hand side. Okay. So you can use these fusion rules and the fact that you can do OPE decomposition of this 4-point function, and that OPE decomposition works on three-point blocks. 3-point blocks are hypergeometric functions, so you can use hypergeometric crossing formulae to work out. So here I've just written on the fusion for the Ramond with one Neveu-Schwarz primary, and there's just 2 terms on the right hand side. You get Ramond with some shifted momentum. And there's some structure function which is given in terms of gamma function. This is where all these funny functions come from at the end of the day. Okay, so everything comes out of hypergeometrics and these gamma functions in this formula. So if you sort of massage this degenerate 4-point functions, in this particular case, you can show that the ratio of these 3-point structure constants satisfies a functional shift relation. Namely, if I take one of the momenta and shift it by IB over 2 with plus minus signs, I get back some ratio of these gamma functions. There's a similar statement for shifting by 1 over 2B. Okay? So you have 4 relations, and you can ask what solves these functional relations. And in fact, the DOZZ formula was determined by figuring out solutions to these 4 relations. Okay? And it's important in these discussions that there actually are relations for shifting with B over 2 and shifting with 1 over 2B. And for those of you who know something about n equals 2 Liouville, this is the piece that's missing in n equals 2 Liouville. Okay. And if you sort of massage this, you can write down the structure constant explicitly, so you can check that there's a solution. And that's the formula that these people derived in the 90s. And that defines the theory for C bigger than 27/2. But as in the bosonic case, there's a second solution, and that second solution allows us to define the theory for C less than 3/2, which is the time-lag regime. Okay, so let me just tell you the answers. So the time-lag regime is parameterized by some sans serif B, and again same multiplets and same degenerate Ramond states. Okay, and again 4 sets of structure constants. Okay. So does someone want to guess what the relation between the structure constants is? Inverses, but with one catch. And if you thought 2 minutes about wordsheet string theory, you'll realize why this catch exists. So the structure constant for the 3 V's turns out to be related to the structure constants of 2 V's and a W by inverse and vice versa. And the even and odd Ramond structure constants get inverted with each other. So it's not quite straight inverses, but there's some diagonal inversion. And there's something I've done here, which is not necessary, but I've done it in interest of both transparency and clarity. I put in 2 parameters which are signs. So eta W and eta R are just plus minus 1. And I put them in for reasons you will see later. For now, nothing in the bootstrap fixes absolute signs. And for now, just take those signs as you might have said they're 1. This is what was done in the bosonic case. I'll just put these signs here for which I will motivate later from the string theory. And this is the result that we derived, and also our friends Beatrix, Vladi, and Janis derived. They're not Fermi number because the Fermi number are linear combinations of even and odd. Yeah. So they're not chiral projections, they're sort of half chiral projections, which is why they're annoying. Yeah. Okay. So this works out, and this was Jian Ming was the one who derived it for us. And we did some checks to make, yes? Yeah, so this C on the left hand side is a C for the time lag theory, and all the C's appearing on the right hand side, on the right hand side are C's of the space lag theory with the parameter B put equal to the space time lag parameter, and the momenta put equal to the time lag momenta with factors of I. So exactly like in the bosonic case, but with some crossing the lines between what gets inverted. Okay. Even and odd is a particular chiral projection on the Ramond vertex operators. So the thing is that the nice Ramond vertex operator, it's related to Matthias's question about how you actually do chiral projections. And this is where things get really messy. In the NS sector, you can do some chiral projections. In the Ramond sector, fermions don't really chirally split, but this is some way of splitting them by thinking about that. All right. Okay. So just to tell you that we actually did some work, and it's not just guessing game. We numerically checked that crossing works. All I'm showing you here is the ratio. Is 2 plots. One, not the ratio. One for one channel and the other for another channel. I've flipped some internal momenta, and these are for some fixed external momenta P1 and P4, and I'm scanning over P2 and P3 in these plots. And if you really squint, you can see that every point has two data points. One is blue and one is purple here, and they lie on top of each other, which says that our structure constants for the time lag theory actually satisfy bootstrap constraints across this range of momenta. Okay. So this is an analog of the calculation that was done 10 years ago by Santa Chiara and Ribot to check the time lag theory does satisfy crossing symmetry. All right. So, and I again emphasize that I put in these signs, which I will come to in a second, but those signs do not show up in the crossing symmetry checks because the crossing symmetry involves products of OP coefficients, so no sign will ever show up. I don't think so, and you will see why I put those signs in a second. Yes, I don't think you get different CFTs. I don't think there's any way to fix those signs. It's a question of how you pick out some branch cuts in this DOCD formula. So there's no physical meaning to the signs, but I will give you one that might be helpful in a second. In the string theory, they do matter. In the CFT, they do not matter. Okay, so I don't know if you could have said, why did Zamolodchikov and then Kostov and Petkova pick those choice of signs for the time-like structure constants? My answer is they didn't have to. They could have picked some other choice. So another branch of the same function. All right. Okay, so now we can get into the weeds and talk about So first things first, we can put together a space like super Liouville theory and a time like super Liouville theory, and as you can see, there's a minus sign. That's the negative kinetic term that you were asking about. And the statement I want to make is that if you sort of take this super Liouville field for the space-like case and the time-like case, and then sort of field redefine them, and then do some further integration by parts in this Lagrangian, you'll get the super JT Lagrangian on the world sheet, which is the statement that Chiming made earlier. The world sheet theory is super JT, but now it's not the target space. But I'm not interested in the classical theory. I want to do the quantum theory. So again, I can take the space-like and time-like cases, and now I have to throw in the super Diffie and cross wild ghosts, so the BC and the beta gamma systems. And it turns out, again, the choice, I cleverly parameterize things so that choice of B being space-like B being the same as time-like B is the right thing. And Matthias's question about GSO projection. There is no chiral -1 to the F in this theory. There's no separate left and right moving fermion numbers. There's a single fermion number. The only thing I can do is a diagonal GSO projection, and therefore construct type 0 theories. So that's the same statement for the C equals 1 minimal string. Okay. The subtleties with the C equals 1 compared to C equals 1 for reasons you will see. So let me define for a second the matter fermion number on the world sheet to be the product of the space-like and time-like Liouville fermion numbers, and then the world sheet fermion number will additionally also have a contribution from the ghosts. And there's a question before I get going, and this is not in the paper. In the paper, we made a particular choice, and this came out in some discussions afterwards with Lorenz, and then we're trying to work this out with Jianming, Beatrix, and Vladi. But so let me tell you the sort of slightly updated story. There's a choice of how you put together the supercurrents to define the world sheet n equals 1 supercurrent. There's one canonical choice, which is basically you add up the space-like and time-like supercurrents from the left and right, which is the first line. Okay, the supercurrents, of course, factorize. Those currents, of course, are holomorphically and anti-holomorphically conserved. You can, however, choose to add up the left currents, but the right currents you can choose to subtract between the space-like and time-like. There's one sign there. Okay. So a priori, we have 4 different string theories you can construct depending on which choice I make for the supercharges. So there are 2 choices here. And there are 2 choices for GSO projection. I can project onto the diagonal GSO with total world sheet fermion number being +1 or total world sheet fermion number being -1. Now, usually, one never talks about this because there's a nice way to just do the diagonal GSO projection. And one just talks about this and then defines the 2 choices. The choice with plus sign is the type 0b theory, and the choice with the minus sign is the type 0a theory. Yeah. So I'm just going to do it this way, and I'm going to just declare that whatever I get are 0a and 0b, and 0a prime and 0b prime. For these 2 choices, the primes will just refer to my 2 choices of the supercurrents. And the last statement just means that whenever I project onto the state with the +1, I will call that the type B theory. Okay, so 0b or 0p prime is world sheet fermion number being +1. Sorry? There's no topological theory on the world sheet, but in the JT context, if they correspond to different topological theories, I can put because of fermion number anomaly in a couple S5K, for example. If you go to 2, 2, you don't actually have a choice of GSO projection because you have a U1 current and you actually have to integrate over the U1 current. I'm coming. So, good thing in the NS sector is all 4 theories have the same physical vertex operator if you stick to -1 picture. Okay, in the -1 picture, it's exactly like in the bosonic theory, now addressed with both the C ghost and with the superconformal ghost. But the representative differs in the 0, picture because in the 0, picture, I have to act with G minus half, G tilde minus half, where G and G tilde are now either primed or unprimed, and G tilde minus half is a minus sign. It doesn't matter. All of them, in all the 4 theories, this is what happens. Because the NS sector doesn't care about, so this is the superconformal primary, it satisfies physical state conditions in 0A, 0B, and in the 0A prime and 0B. And then it's just a question of what my supercurrent is, and I get 2 different vertex representatives of the vertex operators in the BRST cohomology, in the primed and unprimed theories. It's just a relative sign in the last 2 terms. There's no time reversal symmetry in these theories. Then you will see what the relation is in the differences are in the Ramond sector, and you'll see in a second. Yeah, they're not simply related by time reversal. Okay. And the Ramond sector spectrum depends on the sign. So in 2 of them, there are no Ramond states. So for those of you who know about the minimal string, you probably know that the type 0 theory does not have Ramond vertex operators. And with my choice, the 0B prime also doesn't have Ramond vertex operators. The Ramond vertex operators exist in 0B and 0A prime. In 0B, it's this, and 0A prime, it's this. It's just different chiral combinations of space-like and time-like Ramond vertex operators, the choice being given by the fact that I flipped the left-moving guys. In some sense, this is related to what you're asking. This looks like gauging by -1 to the F left. This looks like P-duality. But it's not quite the same thing because there's no -1 to the F left in this theory. Okay. This discussion, part of this discussion exists in the minimal superstring literature, going back to work of, I didn't write the reference here, Shi and Seiberg and Klebanau, Maldasin and Seiberg, but I don't think they actually worked out all 4 of these tricks. They only studied 2 of these examples. Sorry? We are not talking about 2, 2. Yeah. There's no 2, 2 Liouville theory for me to talk about. And 2, 2, if you want to couple it to 2, 2 supergravity, bullshit supergravity, the GSO projection doesn't work this way. GSO projection doesn't work this way because there's a U1 current, you have to sum over all sectors. You have to integrate over all the sectors. This is the famous Uguri-Waffa story of the 2, 2 string, which I'm not talking about. Okay. So let us compute 3-point functions in this theory. And therefore, I can compute them in all the different theories. And now you see that my choice of signs matter. So again, just to highlight something which I'm going to highlight over in interest of time, the inversion statement that I showed you, that the 3-point function of 3 B's gets related to the 3-point function of 2 B's and a W in the time-lag theory, secretly knows about the fact that I have to do picture changing in the worldsheet correlators. Because the vertex operators, if I compute 3-point functions, but in the NS sector, I have to soak up, I have to put 2 vertex operators in -1 picture and 1 vertex operator in the 0 picture. And every 3-point function there's no 3-point function between 2 V's and a fermion by spin conservation, but there's a 3-point function between all three V's, but two V's and a term. And therefore, I think time-like Liouville theory is pretty clever. It seems to know about how worldsheet spin structure sums work. Okay, but so you get constants, but the constants are determined up to these choice of signs. How much time do I have? 5 minutes? Good. Okay. So this is the answer. And I kept all the signs here explicit because I want to tell you something very important about what is expected from matrix models. Good. So Stanford and Witten studied a class of matrix models, dual to n equals 1 T supergravity, and they made the following observations. They also studied many other things in their paper. They also studied examples with time reversal symmetry, which I'm not going to talk about. So I'm just going to talk about the two examples, simple ones, which correspond to type 0A and type 0B JT supergravity, which is basically a choice of fermion boundary conditions. In the type 0B theory, because I'm doing a diagonal GSO projection and projecting to states with -1 to the f equals +1, there's a fermion number symmetry. And perturbative amplitudes in this theory, which are related to volumes of moduli space of super Riemann surfaces, vanish to all orders in perturbation theory. Okay, I don't mean they vanish to tree level. I just mean any endpoint function on any genus G vanishes. The way they prove this, the vanishing on sphere, for sphere amplitude is very easy to explain. A super Riemann surface has, if people remember the modular space of super Riemann surface of genus G, it's -3 plus, and if I put ns punctures, it's a super manifold of dimension -3 plus n slash -2 plus n. There's always one extra fermionic modulus. So when you compute volumes, the fermionic modulus kills you and you get 0. Okay, there's a similar statement for higher genus, but the way they derived it was by computing the 3-point amplitude and then showing that the matrix model satisfies topological recursion. And therefore, since the seed value is 0, everything is 0 to whole higher orders. In fact, you can do something better. You can just look at the spectral curve. And the spectral curve for the 0B theory is Koch-Koch, which is edge-free. And since it's an edge-free spectral curve, it again says that there is no amplitude. There's no physical correlation function that's non-zero. Okay? And this was verified by Clifford Johnson by just taking this choice of spectral curve. So edge-free spectral curves, the claim is there are no perturbative amplitudes. Only amplitudes are non-perturbative. In the 0A theory, there's a fermion number operator, and this is related to this statement that there is a -1 to the f left anomaly. So what you compute are this mod 2 index, and this mod 2 index can be can be non-zero for genus higher than 0. Importantly, in this theory, all tree-level amplitudes are supposed to vanish. I can make them vanish by choosing signs, but the funny thing is I seem to have to make different choice of signs. So I want everything to vanish in the type 0B theory. I want to choose eta w to be -1 and eta r to be +1, which I find very odd. Okay. So we don't have a resolution to this, and something we're trying to do right now is check higher point amplitudes, which are significantly more involved to compute, because in any way you slice it, you end up with having to compute things involving things with, so a 4-point function in an S vector involves 2 operators in -1 picture and 2 operators in 0 picture, which means that I have to compute a whole load of 4-point functions to see why something is vanishing. They vanish in the B. So the statement which was derived was vanishing in the B to 0 limit. But because this spectral curve, this deformed spectral curve, still doesn't have an edge, there's an argument that they also vanish in the deformed theory. It's true that Stanford Witten did not study the deformed theory. They only studied the theory in the B to 0 limit, which is just a Koch spectral curve. All right, so I am almost out of time. So as I say, that we have to engineer some choice of signs to make this work, and I'm somewhat dissatisfied by that statement. We would like to fix this. My philosophy would have been that you should fix the structure constant of the CFT once and for all, and they should be fixed by just in picking a branch which satisfies bootstrap constraints, and that should be the final answer, and the string theory should do what it does given the data. All right, so just let me flash some. So I've mostly reviewed the basic ingredients. We don't have the full duality in place yet, but hopefully that won't take far too long. What I want to highlight is there's something remarkable in this theory, namely that you go through this what might be described as a very simple ingredients, and there's a nice elementary string construction that people were taught Liouville theory, they could just study as their first course in string theory without having to do anything fancy. But you end up with a theory which is supposed to have zero amplitudes in perturbation physics. So everything in this theory is in the non-perturbative physics. Just damn interesting. But it's damn hard to see any of that from the worldsheet. So how do you derive the vanishing theorem for string amplitudes without actually going through detailed computations involving all these new structure concepts? I think one resolution is potentially to try to derive topological recursion directly from the worldsheet, but as far as I know, this has limited success even in the old days, and something that we're thinking about right now. So with that, let me just thank you and apologize for